Good morning, dear students, and hello and welcome to yet another chemistry class. We are learning the lesson Biomolecules, that is 14th chapter of your textbook. Well, yesterday I had taught you about some of the biomolecules. I told you that we are going to learn about carbohydrates, proteins, enzymes, nucleic acids, etc. Right? Yesterday we started with carbohydrates. Now I told you yesterday that carbohydrates are the hydrates of carbon, right? They are polyhydroxyaldehydes or polyhydroxyketones or compound which give such compounds on hydrolysis, right? Then carbohydrates, I told you, they are also called as saccharides because they are sweet. In this, after learning about carbohydrates, we have seen the classification, right? Like mono, poly, oligosaccharides, monosaccharides we have learned. Then after that, we discussed about one of the most important carbohydrate, that is glucose. I told you the structure of glucose. Today before we begin with, in short, we'll be dealing with the structure of glucose. Then there are two methods which we discussed yesterday for the preparation of glucose, right, from sucrose and from starch. Then we have also deduced the structure of glucose by treating glucose with HI, mild oxidizing agent like Br, and etc. This is what we have done in the yesterday's session. Okay, dear students, today we'll be talking something about optical activity in this compounds. If time permits, we'll also be starting with fructose, one more carbohydrate. Okay, so before we begin with, this is the structure of glucose, right? So how do we write the structure of glucose? Is you have 1, 2, 3, 4, 5, 6 carbons in a line, and the difference lies on the third carbon, right? First you need to draw CHO at the first position, CH2, OH at the last, and at the third position you'll have HOH in this form. Okay, so today we'll be discussing about the optical isomerism in glucose. Well, as we start with this, dear students, there are four chiral carbons in glucose, right? There are four chiral carbons in glucose. And here now we'll see the optical activity in glucose, right? Okay. So, structural formula of glucose show that it contains four chiral carbon atoms. What is chiral carbon? You have already learned this. Carbon which is attached to all different groups. Okay, that carbon is known as chiral carbon atom. And when we consider glucose, you have four chiral carbons in glucose. Every chiral carbon can have two distinct spatial arrangement of groups around it. Two distinct configurations are possible for each of the four carbons of glucose. Glucose, children, is an optically active compound and has its specific rotation. Due to its dextrorotation, glucose is also called as dextrose because it rotates the plane polarized right to right hand side, and it is designated by plus glucose or a small d. Here you have to pay attention. That is when we deal with rotation, okay, dextro or levo, we write a small d. Small d for dextrose, small l for levo rotation. So from in discussing about optical isomerism in glucose, first and foremost thing you should know that there are four chiral carbons in it, and glucose is an optically active compound, and what it does, it rotates the plane of plane polarized right towards the right, and hence it is designated as डी ग्लुकोज. आणि इथे लक्षात ठेवण्याची गोष्ट अशी की वी राईट स्मॉल डी अँड स्मॉल एल फॉर optically active compounds. Then this is the structure. This is your Fisher projection. The thing you can see on your slide is a Fisher's projection formula for glucose, gluconic acid and saccharic acid. Well, students, this structure in the beginning only I've shown you on the slide. The difference lies in the third carbon, right? And there are four chiral carbons in it. The second structure is of gluconic acid. At the first position, you will have COOH over here. And the third is of saccharic acid. First and sixth position, both you have a acidic group present. So this is glucose, gluconic acid and saccharic acid. And this particular is the Fisher's projection formula for glucose, gluconic acid and saccharic acid. Now, dear students, we'll talk about what exactly is D and L configuration system. Here we emphasize is capital D and capital L. Okay, capital D आहे आणि capital L हे आपण केव्हा देतो हे आपण पाहणार आहोत. Now on the screen you can see the structure of glyceraldehyde. Okay, you can see the structure of glyceraldehyde. One is T glyceraldehyde whereas the other one is L. D plus glyceraldehyde, capital D, capital L minus glyceraldehyde. And this is the structure of glyceraldehyde. It consists of one chiral carbon. आता इथे पहा chiral carbon म्हणजे हा carbon आहे and which is attached to all four different groups. Okay, now we'll see what is D and L. The prefixes, dear students, capital D or L in the name of the compound indicates reflective configuration of stereoisomers. It's referred to a particular enantiomer of glyceraldehyde. Enantiomers are the mirror images. Glyceraldehyde has one chiral carbon at C2. I told you glyceraldehyde consists of one chiral carbon. This is the chiral carbon over here, and it exists as two enantiomers. In one form, OH is towards the right hand side, and in the other form, OH is towards the left hand side. So, students, if OH is at the right hand side, we call it as T plus glyceraldehyde, and here we have a capital dip. And if OH is towards the left hand side, we call it as L glyceraldehyde. Okay, so OH on the right hand side, we'll call it as D glyceraldehyde. OH to the left hand side, we'll write it as L and minus glyceraldehyde. Okay, then we'll see in the next slide one example. Okay, plus glyceraldehyde is represented by Fisher's projection formula having OH group attached to C2 on right hand side, and this configuration is denoted by the symbol capital D. As I told you, if it is on the right hand side, it is denoted by capital D and plus sign. We'll call it as plus glyceraldehyde. Similarly, configuration of minus glyceraldehyde is denoted by the symbol capital L. All the compounds which can be correlated by a series of chemical reactions plus minus glyceraldehyde are said to have D configuration. The compounds which are chemically correlated to minus glyceraldehyde are said to have L configuration. This is the system of relative configurations of chiral compounds. So based on the structure of glyceraldehyde, we will tell if the OH group is towards the right hand side, we'll call it as D, and plus symbol will put glyceraldehyde, sign will put, and if it is on the left, it would be minus or L glyceraldehyde. Now, for example, if you want to know whether it is D or L configuration for a particular monosaccharide, what you have to do is, students, a monosaccharide is design D or L configuration on the basis of the configuration of the lowest chiral carbon in its Fisher projection formula. So glyceraldehyde structure we have to consider, and the thing that is, if it is on right hand side, we'll call it as D. Now you can see this is the structure of glyceraldehyde and this is your monosaccharide, right? You have to see the second last carbon. We have seen the fifth one. Now here fifth carbon मध्ये OH जो आहे तो right hand side ला आहे. ओके, मग जो तो राईट हँड साइडला आहे तर आपण त्याला काय म्हणणार, डी, आणि साइन कुठली देणार, प्लस, आणि डी कुठला असणार आहे, कॅपिटल डी प्लस साइन, अँड दिस इज द स्ट्रक्चर ऑफ ग्लुकोज. सो यू कंपेअर दिस विथ द स्ट्रक्चर ऑफ ग्लिसरॉल्डिहाइड. आणि कुठला कार्बन आपण कन्सिडर करतो, सेकंड लास्ट, दॅट इज द फिफ्थ. And now in case if the OH was in on this side, that is left hand side, it would have been L. Now let us take one example. This problem is there in your textbook. You can go through your textbook also. So here on the screen you can see two structures. One is of triose and other is of ribose. आता आपल्याला काय करायचं आहे, ह्यांना डी आणि एल कॉन्फिगरेशन्स असाइन करायचे. सो असाइन डी एंड एल कॉन्फिगरेशन्स टू द फॉलोइंग मोनोसॅकराइड. आता तुम्ही पहिली स्टेप काय करणार, you've seen the structure, right? Now what you are going to do is see how many chiral carbons are there in the structure. Well, in triose has two chiral carbons, that is C2 and C3. triose मध्ये दोन chiral carbon आहेत, एक आहे C2 वरती आणि एक आहे C3 वरती. So the given Fisher projection formula of triose has OH group at the lowest C3 chiral carbon on the right side. आता हा जो कार्बन आहे थर्ड वाला, the OH group over here is present on which side, your students? On the right hand side, right? So therefore it is known as the triose, right? Whereas in ribose structure, the OH group, how many chiral carbons are there? 1, 2 and 3 chiral carbons. That is carbon number 2, carbon number 3 and carbon number 4. The given Fisher projection formula for ribose has OH group at the lowest C4 chiral carbon on the left hand side. So it is known as L ribose. जर OH left hand side ला आहे, so it is known as L, that is capital L, and if it is on the right hand side, we write it as capital D. So these are the configurations to be assigned. I hope you are clear with this. Now dear students, we move on to the ring structure of glucose. We have seen the straight structure of glucose, right? Now we will be moving on to the ring structure of glucose. So on the basis of chemical evidences, stereostructure of D-glucose was represented by the Fisher projection formula. The formula which you can see on your slide, see on your screen, is the Fisher projection formula. Okay. Now, glucose, however, was found to exhibit some more chemical properties which could not be explained on the basis of this structure. फिशर प्रोजेक्शन फॉर्म्युला मधून असे काही केमिकल प्रॉपर्टीज होते जे एक्सप्लेन करता आली नाहीत, अँड फॉर दॅट reason we had to study the ring structure of glucose. So it was necessary to write down another structure of glucose. So what is the other structure? How is it formed? That we are going to study now. Okay, dear students. So here on the screen you can see the Fisher's projection formula for glucose. Okay. Then how does it get converted into the ring form? That we are going to study. So glucose is found to have two cyclic structures. See, glucose also has two cyclic structure, that is this sixth and seventh one, which are in equilibrium with each other through open chain structure in aqueous solution. So you will have two structures of glucose, right? And dear students, the difference in both the structures, see the name is alpha D plus glucose and beta D plus glucose. Now, what is the difference between these two structures? We'll be learning slowly and steadily. So, what is happening in this is the OH group on the fifth carbon goes and attaches. See here in the structure, the OH group on the fifth carbon will go and attach on the first carbon. And if the OH is on the right hand side, it is called alpha D glucose. And if it is on the left hand side, then it is beta D glucose. We will learn this in detail now. See, the ring structure of glucose is formed by reaction between the formyl group is CHO group, and the alcoholic group at C5. Thus, the ring is a hemiacetal structure. So, as I told you in this slide, the OH goes and attaches on this formyl group, right? This OH will go and attach over here, right? So the O is shown over here, okay? So this structure, these structures are known as hemiacetal structures. So what is happening? The reaction between the formyl group and the alcoholic group at C5 takes place, and the structure which is formed is a hemiacetal structure. Okay. Thus, the ring is a hemiacetal structure. The two hemiacetal structure differs only in the configuration of C1. See students, there is just a difference between the carbon number 1. In alpha D glucose, the OH is towards the right. In beta D glucose, OH कुठल्या साईडला आहे left. So the difference is just in the carbon number 1. The additional chiral center resulting from ring closure. The two ring structures are called alpha and beta anomers of glucose, and C1 is known as the anomeric carbon. You have to remember that C1 is known as the anomeric carbon, and there is just the difference between the carbon number 1. One is known as alpha D glucose and other is known as beta D glucose, and they are anomers of each other. Now, the ring of the cyclic structure of glucose contains 5 carbons and 1 oxygen. Now, when we move on to the ring structure, it consists of 5 carbons and 1 oxygen. Thus, it resembles six-membered ring, and that ring is known as pyranose. And since it is in analomy with pyranose, it is also called as glucopyranose. See, this is the structure of pyrene. We will be coming to this slide. This is the structure of pyrene, and since it resembles this structure, we call it as glucopyranose. So we have seen how from Fisher's formula we turn on to a cyclic structure which resembles pyrene, and hence glucose is, that structure of glucose is also called as glucopyranose. Well, now Howard formula, the pyranose ring is considered to be in a perpendicular plane with respect to the plane of paper. Now this will be learning with the help of the structure. The lower side of the ring is known as the alpha side and the upper side is known as beta. Now can you see the structure? Okay, in this structure, the lower side is known as the alpha side, whereas the upper side is known as the beta side. Okay, the alpha anomer has its anomeric hydroxyl group on the alpha side, whereas beta anomer has anomeric OH group on the beta side. The group which appears on the right side in the Fisher projection formula appears on alpha side in the Howard's formula and vice versa. So this is the Howard's formula. Now I'll tell you how can we draw the Howard's formula of glucose based on the Fisher's formula. So previously we have seen that the OH group on the fifth carbon will go and attach on the first carbon, right? So what would happen is either you will get this OH group on the right hand side or on the left hand side. So the difference is only in the first place. They are known as anomeric carbons, right? So you will get either alpha D glucose or beta D glucose. Now we need to write it in a cyclic form. So how do we write? Now you concentrate on the first structure. म्हणजे अल्फा डी प्लस ग्लुकोजचा स्ट्रक्चर हा रिंग मध्ये कसा कन्वर्ट होतो हे मी दाखवते. सो what you have to do is all the groups which are on the right hand side will go on the alpha side. Now check, dear student. This is your first carbon, second, third, fourth, fifth and sixth. Okay. So here you will have first, second, third, fourth, fifth and sixth position. So whatever is present on the right hand side will go on the alpha side. म्हणजे खालच्या साईडला येईल. That is, see, this is the OH on the first carbon. This OH goes over here. Second carbon चा OH इथे खाली गेला alpha side. Then third चा hydrogen इथे आला. Fourth चा OH came over here. And on the fifth carbon, the bulkier group, that is CH2OH, would be up, hydrogen would be डाउन. म्हणजेच काय की ज्यावेळेस आपण रिंग मध्ये कन्वर्ट करतोय तर व्हॉट वी आर डुईंग ऑल द कंपाउंड्स ऑन द राइट हँड साइड विल गो ऑन द डाउनवर्ड्स पोझिशन, दॅट इज ऑन द अल्फा साइड. ओके, सो दिस इज योर अल्फा डी ग्लुकोज का स्ट्रक्चर and whereas the other one, that is beta D glucose structure, same thing you are going to do over here also. काय करूयात आपण, all the groups which are on the right hand side will come on the alpha side of the structure. So hydrogen जो पहिला कार्बन वर आहे तो खाली जाईल. Then you have OH, it will go on the second group. Then you have H, it will go over here. OH down. And here on the fifth carbon, the bulkier group will go up and you have a hydrogen over here. So this is glucopyranose ka structure. Why? Because it resembles pyrene ring, right? So this is also known as alpha D, capital D plus glucopyranose and beta D plus glucopyranose. Very good. If OH group is on the downwards position, we call it alpha, and if it is on the upper side, it is known as beta glucopyranose. I hope you have understood what I am trying to tell. Please draw the structures in your notebook. Unless and until you draw both Fisher's and Howard's projection formula and actually draw it in your notebook, it's very difficult for you to understand. But if you follow this trick, I hope it would be easier for you. So just recall what I need to do is all the groups which are present on the right hand side will go down the ring, that is on the alpha side. Hope you have understood it. Now we'll talk something about the reducing nature of glucose. See, hemiacetal group of glucopyranose structure is a potential aldehyde group. We know the hemiacetal group of glucopyranose is an aldehyde group. So it imparts reducing properties to glucose, and त्याच्यामुळे ग्लुकोजला कुठल्या प्रॉपर्टीज येतात, reducing properties. Thus glucose gives positive Tollens test and positive Felling's test. Reducing sugar have aldehyde group which is free. This point you have to remember. So today we'll learn about the last structure, that is yet another carbohydrate structure, which is fructose. So we'll see the structure of fructose after learning glucose now. So the representation of fructose structure. The molecular formula is same, but the structural representation here is different because glucose had an aldehyde group fructose have a ketonic group present. See, the molecular formula is C6H12O6 and is a levorotatory ketohexose. That means it will rotate the plane of plain polarized light towards the left. Fructose is also called levose due to its levorotation. Okay, due to levorotation is also known as levulose. Being an beta hydroxy ketone compound, fructose is a reducing sugar. So fructose is a reducing sugar. In free state, it exists as a mixture of fructopyranose and fructofuranose. In combined state, fructose is found in the form of fructofuranose ring structure, just like pyranose, glucopyranose, fructose also form a fructofuranose structure. Now, why furane? Because it resembles furanose ring. Okay. So the name furanose is given by analogy with furane, a five-membered heterocyclic compound. So this is the structure of furane. As we have seen the structure of pyrene, this is the structure of furane. So since it resembles furane, this is known as fructofuranose. That glucose structure resembles pyrene, so it was known as pyranose, glucopyranose, and fructose resembles furane, so it is known as furanose. Okay, so how do we write it in Fisher's formula? It's just the same, dear students, like glucose only, but the difference over here is here you have on the second carbon C double bond O. That is, you will have a ketonic group over here. This is the structure of fructose. Well, now how do we convert it into fructofuranous form? It's just same as I told you just now about glucose. So this is your open chain structure of fructose. So कसा करणार? 1, 2, 3, 4, 5 and 6. 6 carbons in a line. At the starting you have CH2OH, CH2OH. हे same आहे. मग second position you'll have C double bond O. So this is your open chain structure of. इथे पण आता काय होतंय, the OH group of the fifth carbon will go and attach on the second position over on this carbon, and so you will get alpha D fructofuranose and beta D fructofuranose. So alpha if OH group is on the right hand side, beta if the OH group is present on left hand side. This can now be converted into a ring structure, that is furanous form. Okay, so same way ज्या गोष्टी राईट हँड साईडला आहेत, फॉर एक्झाम्पल OH, H, OH या सगळ्या कुठे जातील तर अल्फा साईडला जातील, म्हणजे खालती जातील. OH, H, OH and H and the bulkier group would be on the top. Same is the case over here, right? So CH2OH, H, OH, and you'll have CH2OH and H over here. So this is alpha D fructofuranose and beta D fructofuranose. So far, dear students, we have seen the Howard's and the Fisher's projection formula for glucose and fructose. You need to draw the structures in your notebook, then and then only it can be understood. So dear students, please see to it that you all practice the structures, draw the structures again and again. Unless and until you draw all the structures, it won't be helpful. So please see that you practice the structures. In tomorrow's lecture, we'll continue with glycosidic bond and some more